Good day, students. Welcome to part 2 on our review on integration by parts and substitution. So let's go ahead and take a look at question number 1. We are to evaluate the following indefinite integral, the integral of x root x minus 1 dx. Okay, I'm going to evaluate this integral using two methods. The first method will be a combination of integration by parts and substitution, and the second method will just be done using use substitution. All right, so method one is longer. So method one is integration by parts, integration by parts, and substitution. All right, so let's go ahead and do this using integration by parts. So let's go write down what the formula is for integration by parts, just to refresh our memory. So the formula for integration by parts is the integral of u dv equals uv minus the integral of v du. All right, so if we take a look at this integral right here, we're going to call u x, and dv is going to be the square root of x minus 1 dx. Okay, so let's rewrite the integral. So we have the integral of x. I can write root x minus 1 as a quantity x minus 1 raised to the 1/2 dx. So I'm going to call this my u, and this piece will be my dv. All right, now why did I call this dv and call this u? If you think about it, if we differentiated this quantity right here, we'll have a much more complicated expression. And then we integrate this, this becomes x squared over 2. So if I focus on integrating this, which is very easy to integrate, I'll end up with an expression that I can easily differentiate, because this u basically becomes 1 upon differentiation. All right, so this is the best order for selection here. Now, another thing to note, using LIPET, these two are powers, but this has a higher power, so in most cases, the one with the fractional power should be the dv piece. Okay, so we have u equals x, and dv equals x minus 1 to the 1/2. Now, we have u and dv. In this formula, I need u, v, and du. All right, so u and du needs to be determined. So let's find what du is. I'll differentiate this side using differential. So du is simply going to be derivative of x, which is 1 dx. So there goes du. And to find v, I'll simply integrate both sides of this equation. If I integrate dv, I'll get v. Imagine there's a 1 here, so just integrate that. And then I'll have to find the antiderivative of x minus 1 raised to the 1/2 dx. Okay? I was supposed to put a dx here before, because this entire piece is dv. Okay? All right, so let's go ahead and integrate that. How do we integrate this expression? To integrate this, we can use use substitution. How do I know to use use substitution? Because if you differentiate the inner function of this composite function right here, you end up with a multiple of the other function, which is 1 dx. Okay, so that's a telltale sign to use integration by substitution. So we're going to call u x minus 1, and then when we differentiate both sides, we have the u equals derivative of x, which is 1 dx. Okay, now we're still looking for v, so we can plug it into the integration by parts formula. Note we already have the u, so we just need to find v for this spot and this spot. Okay, so now using use substitution to find v, we're going to have the integral of u to the 1/2, replacing x minus 1 with the u value to the 1/2. Dx now simply becomes du. is a perfect du because we do not have to multiply by any constant to get the dx replacement. Alright, so what's the antiderivative of u to the 1/2? You use the power rule. So you're going to have u to the 1/2 plus 1. 1/2 plus 1 is 1/2 plus 2 over 2, which is 3 over 2. And then you put the same thing on the denominator, 3 over 2, as the power. Alright? And now we're going to multiply the numerator by the reciprocal of the denominator. So we have 2/3 u to the 3 over 2. Okay? So now what is v? V, we know that everything else is in terms of x, so we need to plug in the value of u right back into this expression. Okay, so we're going to have 2/3 instead of u is going to be x minus 1. Remember, earlier we called u x minus 1 so we could integrate using substitution, so we have to plug it back. 2/3 times x minus 1 to the 3 over 2. Now we have everything we need to use the integration by parts formula. So let's rewrite the integration by parts formula again. The integral of u dv equals uv minus the integral of v du. Alright, so let's rewrite the problem. The original problem was the integral of x times the square root of x minus 1 dx is equal to uv. U is x, v is this term we got right here that we had to use substitution to find, which is 2/3 x minus 1 to the 3/2 minus the integral of v again, 2/3 x minus 1 to the 3/2 du is just simply dx. Okay. All right, let's go ahead and simplify this expression. So uv, we can write it as 2/3 x times x minus 1 to the 3/2 minus this 2/3 can be factored out, so we have 2/3 times the integral of x minus 1 to the 3/2 dx. All right, now let's shift our attention to the integral of v du piece that we have here. Now, how can we evaluate this integral? If you notice, we cannot evaluate this integral using u substitution again, because if we differentiate the inner function of this composite function, we have a multiple of the other function, which is 1 dx. All right. So to integrate this, we're just going to call u the inner function of the composite function x minus 1. If you differentiate that, the u is equal to dx, like we did before. All right. So let's put that in. So we're gonna still we're still evaluating this integral right here. So we have 2/3 times x minus 1 to the 3/2 minus, and we'll write this as 2/3 times the integral of u instead of x minus 1, call u to the 3 over 2 dx, because I'm sorry, du. Okay, du is equal to dx. It's basically the same thing, but we have to be consistent with our variables. So this is du. All right, let's see. So to evaluate this, we're simply going to use a power rule. So this is going to become minus 2/3. The antiderivative of u to the 2/3 is u to the, you add 1 to that, that's the same thing as adding 2 over 2, so it's 5 over 2 divided by the value of the power, which is 5 over 2. Okay? 2/3 x times x minus 1 to the 3/2. And then let's just simplify this a little bit more, and then we'll be done. Okay? So this becomes, let's see, 2/3 x times x minus 1 to the 3/2 minus, now multiply 2/3 by the reciprocal of 5 over 2, which is 2 over 5. So if you multiply that, you end up with 4 over 15. And then what is u? U is x minus 1, right? So let's put that back, x minus 1 to the 5/2. Okay? plus c. Now this is your final answer, but we could simplify it a little bit more, make it look pretty. So let's go ahead and simplify this. I'm just going to use some algebraic steps to uh, condense this expression. All right. So I can write this expression as 2/3 x times x minus 1 to the 3/2 minus um, 4/15, 4 over 15. And then I can break this up into x minus 1 to the 3/2 times x minus 1 to the 2 over 2, which is just 1. Okay, so to the 1 plus c. All right, so what I'm just using is the reverse of the product property of exponents. When you multiply exponents, you add the powers. So if I did the reverse, I just broke this up into its composite parts. 3 over 2 plus 2 over 2. 2 over 2 is 1. Okay, the reason why I selected to extract 3 over 2 from 5 over 2 is because I wanted to have a match, an exponential match with this term right here. Okay, so I can now factor out, let's see what's common. 2 and 2 are common in here, so I can take out a 2 and also a 3 from both terms. And I can also take out x minus 1 to the 3/2. Okay, so in this term right here, all that will be left is just simply x. Okay, minus, if I factor out 2/3 from this fraction right here, the numerator is divided by 2, so you're left with 2. The denominator is divided by 3, so you're left with 5. And then this was common, right? X minus 1 to the 3/2, we factored it out, so this is gone, and you're left with x minus 1. Okay, that entire term plus c. So let's just combine these terms here, and that should give us the final answer. Let's go ahead and do that. So we have 2/3 times x minus 1 to the 3/2 times, now we can put this x over 1, multiply both sides by 5 and 5, top and bottom. So we have the same LCD, and then we can combine it with this term right here. And then I'm going to distribute this 2/5 to these two terms over here, okay? So we're going to have 5x minus 2x, and then negative 2 times positive 1 is plus 2. And then that entire expression divided by the common denominator that they both share, which is 5. Okay, so put a 5 down here, plus c. And our final answer is going to be 2/3 times x minus 1 to the 3/2 times 5x minus 2x is, let's see, 3x plus 2 over 5 plus c. Okay? Oh yeah, we can also bring out this 1/5 right here. Let's make it look nicer. So this is, we can rewrite this as 2 over 15 times x minus 1 to the 3/2 times 3x plus 2 plus c. All right, so that's your final answer. All right, let's take a look at method 2. We're going to do the same problem. In method 2, we're just going to use substitution only. Okay, unlike the other one where we use two different methods. This one we're going to use only use substitution. All right, so we're evaluating the same integral, which is the integral of x root x minus 1 dx. All right, so with this one, I'm going to call my u the square root of x minus 1, so that can enable me substitute this with u. Now, how about this x piece? To get the x piece isolated, I have to isolate x here. So to do that, I'll square both sides first. U squared equals x minus 1, and then add 1 to both sides. You can clearly see that u squared plus 1 equals x. To get the dx piece, I'll simply differentiate both sides this equation implicitly. So if I differentiate this side, I'm going to have 2u du, derivative of 1 is 0, equals derivative of x is just 1 dx. Okay, so a nice substitution happening here. So I'm going to make use of 1, equation 1, equation 2, and equation 3 to express this integral in terms of only u. Alright, so this is going to become the integral, the x piece becomes u squared plus 1, and then the square root of x minus 1 piece becomes u, and then dx, don't forget the 2 is 2u du. Okay? Now we can factor out a 2, take out 2, and then distribute the u's. So this u times this u together as u squared, and if I distribute it to this, I'll have u to the 4th plus u squared. Okay, so that du. So we can see how easy this is compared to the other method. Now what I'm going to do is integrate this, evaluate this integral using the power rule. So this is now going to become 2 times, if you integrate this using the power is u to the 5th over 5, plus, integrating this with the power rule is u to the 3rd over 3, plus c. Okay? Now let's plug in back the values. But before we do that, I can factor out, if you notice, I can factor out u to the 3rd from these two terms, right? The small of the two exponents can be factored out. So we have 2u to the 3rd times u squared over 5 plus 1 over 3 plus c. Okay? And then let's put back in, or let's, we can combine these two fractions while we're at it. So we can multiply this by 3, top and bottom, and then multiply this by 5. So we're going to have 2u to the 3rd, try that again, 2u to the 3rd times 3u squared plus 5 over 15 plus c. Alright? And we can write this, we can also factor out this 15, so we're going to have 2u to the 3rd, well actually 2 over 15, u to the 3rd times 3u squared plus 5. Okay? Are we done? Absolutely not. Remember, the original problem was in terms of x, right? So we're going to make our substitutions here. Let's put in the value of x back into the u. We know that x is equal to, u is equal to x minus 1 to the 1/2. So let's go ahead and put that back in here. So on this term on the outside, we have 2 over 15 brackets. U is the square root of x minus 1, which is the same thing as x minus 1 raised to the 1/2. So we raise that to the 3rd power. Times 3. Remember what u square is? U square is x minus 1, right? Or the square of x minus 1. So the square and square root cancels out. So u square is simply x minus 1 plus 5 plus c. All right? Let's see, let's simplify this. One more step using elementary algebra here. So 2 over 15. Now, this is, we can write this as 3 over 1. So using the power property of exponents, you just simply multiply the powers. X minus 1 to the 3 over 2. And then here, distribute the 3 to the x and the 1. So you have 3x minus 3 plus 5. So that yields 3x minus 3 plus 5 is plus 2 plus c. And there goes your final answer. So this is just another method of evaluating the integral using u substitution only, as opposed to the other one where we use u substitution and integration by parts simultaneously. Okay, so there you have it. Good day, students. Welcome to part 1 on our review on integration techniques. We're going to be going over a problem that involves integration by parts and substitution. Okay, so the instructions are for us to evaluate the following integral. Evaluate the indefinite integral of x to the 3rd over the square root of x squared plus 1 dx. Okay, Now I'm going to be doing this integral using two methods. I'll do the long way using integration by parts and substitution. Then I'll show you another elegant approach that can be used to evaluate this integral. Okay? So method one, we're going to use we're going to do integration by parts and substitution. Okay? All right. So what I'm going to do here is set this integral in such a way that I can do integration by parts. So if I express this integral in the following format, x squared times x divided by the square root of x squared plus 1 dx, what you notice is that it's easy for me to find an antiderivative of this expression right here. I'm using u substitution, and then I can differentiate this with ease. Had I used the reverse process, call this dv and call this u, then when I differentiate this, it looks very complicated and it makes our life much more difficult. All right. So in this case, I'm going to call my u. My u is going to be x squared, and my dv is going to be x divided by the square root of x squared plus 1 dx. All right. Now remember the formula for integration by parts. Let's rewrite it here. Is the integral of u dv equals uv minus the integral of v du. All right. So in this formula, we know that u is x squared. So all we just need to find is v and du. All right. So let's find du first. We'll accomplish that by differentiating u using differentials. If I differentiate u, I'm going to have 1 times du. Applying the power rule here, I'll have 2x dx as a derivative of x squared. All right, let's shift our attention to dv. In order to figure out what v is, I will have to find the antiderivative of this side of the equation. Okay, so v basically is the antiderivative of x divided by the square root of x squared plus 1 dx. Okay, now in order to evaluate this integral right here, we'll have to use u substitution or integration by substitution. Since I already have my u alphabet taken, how about we use w here? All right, so to evaluate this integral, if you notice, if I differentiate x squared, I'll have a multiple of x, namely 2x. So I'm going to call the innermost function of my composite function 1 over x squared plus 1. I'm going to call that w. So let w equals x squared plus 1. Now if I differentiate that, that tells me that dw is equal to 2x dx. Okay, notice we have x dx over here, so that means that I need to get x dx by itself. To accomplish that, I need to divide both sides by 2, and then I'll have dw over 2 is equal to x dx. Now we're ready to make our substitution. Okay, so we're still trying to figure out what v is. We have to evaluate this integral to figure out what v is. So we're going to have the integral of this piece, 1 over the square root of x squared plus 1, can be written as 1 over the square root of u, or we're calling it w this time. And then our x dx over here, our x dx will become dw over 2. Okay, so dw over 2. Now let's rewrite this in such a way that's easy for us to evaluate the integral. So in order to do that, we're going to use the properties of exponent, the reciprocal property of exponents, and the special case of the nth root. So we're going to have this integral of w to the negative 1/2. This 2 can be factored out, so we'll have a 1/2 in front here, dw. All right. And we can clearly see that this is easy to integrate. If we integrate this using the power rule, we're going to have 1/2 times, we just add 1 to the power and divide by, add 1 to the power. So negative 1/2 plus 1 is the same thing as adding 2 over 2, so you're going to have positive 1/2, and you divide by that value, which is also positive 1/2. All right, and then when you multiply the numerator by the reciprocal of the denominator, you find out that your antiderivative v is w to the 1/2. Okay, so we know what v is. V is w to the 1/2. So we have to do some work in order to get what that value is. But we note that we're working with x's, right? So we have to express v in terms of the same variable as du and x and dv. So we need to change this back. In order to do that, we're just simply going to replace w with its initial value, which is x squared plus 1. So w is equal to x squared plus 1 raised to the 1/2 power. Okay? Now we're ready to apply integration by parts formula. So we recall what the integration by parts formula is. Let me partition my workspace here so we don't get confused. Put it down here. So I'm going to write my integration by parts formula again so we can have everything organized. Okay? So integration by parts formula, we have the integral of u dv equals uv minus the integral of v du. Alright? So we know that u is x squared. V that took us so long to find is x squared plus 1 raised to the 1/2. So that's uv minus the integral of v, which is same thing, x squared plus 1 raised to the 1/2 du, that's 2x dx. Okay? All right, let's take a look at this integral expression for a second. Do you think we can do this by integrating by parts or by use substitution? If you notice the inner function of this radical function right here, if you differentiate it, do we get a multiple of this other function? The answer is yes. So we do not need integration by parts. We can use the reverse of the chain rule or integration by substitution to evaluate this piece over here. Okay? Alright, so to do that, all we're just simply going to do is we're going to call u the inner function of this composite function right here, which is x squared plus 1. And then du is going to be 2x dx. This is a perfect case because we do not have to divide by anything. This du right here is a perfect replacement for this 2x dx piece. Alright? So now let's put it back into the integral. So it's going to become x squared times x squared plus 1 raised to the 1/2 minus the integral of u to the 1/2, replacing this x squared plus 1 with u, and then 2x dx is nicely replaced with du. Now we can apply the power rule to evaluate this integral right here. If we do that, we're going to have, it's going to become x squared times x squared plus 1 to the 1/2 minus, applying the power rule to this expression, we'll have u to the 3/2 over 3/2. Okay? And plus the c constant. Now we notice that our variable isn't originally what it was, so we need to replace what u is to express this whole function in terms of x. We know that u is x squared plus 1. Alright, so let's apply that back. So our solution is going to be x squared times x squared plus 1 raised to the 1/2 minus, you multiply the numerator by the reciprocal of the denominator, we have 2/3. And then u becomes x squared plus 1 raised to the 3/2 plus c. Alright, so there is your answer. You can leave it like this, but let's make it look pretty. Okay, let's beautify it a little bit with some algebraic steps. Okay, so you can stop here, but I'm going to take it a little bit further, make it look nice. You notice that we can make a factorization here. What if I write this expression like this? What if I wrote it like x squared times the square root of x squared plus 1 minus 2/3. Now, if you think about 3/2 is 1.5, right? So x squared raised to the first power is simply x squared plus 1 raised to the 1, but we don't have to put that. And then the 1/2 piece is square root of x squared plus 1 plus c. Now we can factor out the square root of x squared plus 1, right? Let's go ahead and do that. Factor out that radical piece. So we have the square root of x squared plus 1 times x squared minus, you can distribute this negative 2 to the numerator. We have minus 2x squared minus 2 over 3. Okay, plus c. And then we can find the LCD here. Just multiply this by 3 top and bottom. 3 over 3. And if we simplify, we're going to have the square root of x squared plus 1 times x squared minus 2x squared is just simply x squared minus 2 over 3 plus c. And there goes your final answer. Okay, so that's that. All right, you notice how long it took us? Well, let me show you another way of doing this same problem, much more elegant and fast. You don't need to use substitution and integration by parts. So method two, we're going to find the integral of the same expression, okay? All right, so we're integrating the same expression. So we're going to find, let's see here, the integral of x to the third divided by the square root of x squared plus 1 dx. Okay, now let's make some substitutions here. Now, how about we say, let's call u the square root of x squared plus 1. Okay, if we square both sides, we'll have u squared equals x squared plus 1. If we subtract 1 from both sides, we have u squared minus 1 equals x squared. Okay, so we basically have a replacement for x squared plus 1. Now, how about the x situation? How are we going to do that? Well, we'll just simply differentiate this, right? So if we differentiate this, we're going to have 2u du equals 2x dx. All right? So if we can express this in such a way that we have x dx isolated, then we should be able to evaluate the integral. You notice that there are two 2's present, and we want x, we could get x dx by itself. So how about we go ahead and divide both sides by 2 here. Divide by 2, divide by 2. And then we have u du equals x dx. Okay? All right, now let's go ahead and make the substitution. You'll be impressed to see how easy this is going to be. So we're going to have, let me write it in a way that makes it easy for you to understand. So this will be the integral of x squared over the square root of x squared plus 1 times x dx. Okay? All right, let's make our substitution. We know that x squared is u squared minus 1. So we replace the numerator with u squared minus 1 over the denominator x squared plus 1. The square root of x squared plus 1 is simply what? It's simply u, right? So let's call that u. And then x dx is what? X dx is u du. All right? Now let's take a look at this expression. What can be done here? You notice that the u's can cancel out. And we're going to have the integral of u squared minus 1 du. Okay? Now we can use the power rule here. It's pretty straightforward to evaluate. So this becomes u to the third over 3 minus u plus c. Okay? Now remember that the original problem was in terms of x's, right? So we now have to put our x's back into the equation. Wherever we see u, we're going to put the square root of x squared plus 1. Okay, so we're going to have the square root of x squared plus 1 to the third power over 3 minus the square root of x squared plus 1 plus c. Okay, now let's do some cosmetics here to make this problem look pretty. So what we're going to do is rewrite this in the following format. I'm just going to simplify it a little bit. So this is going to become, you can write it as the square root of x squared plus 1 square times the square root of x squared plus 1 over 3 minus, we can find the LCD in this situation here, so we can combine the two fractions. So multiply, put this over 1, multiply by 3 top and bottom. 3 times the square root of x squared plus 1 over 3. Okay, so you notice this is to the third power, so I just basically split it up. I took the first two, so I can cancel this out, and then I have root x squared plus 1. Okay, just basically applying the properties of exponents here. Alright, so let's see. The square root of x squared plus 1 can be factored from both sides. So, but just a side note, this is good enough. This is an answer. You can leave it like this. I just want to make it look nice, okay? Just simplify a little bit further. So I factor out the square root of x squared plus 1 from both sides. So I'm going to have the square root of x squared plus 1. Now this square and this square root cancels out, so we're left with x squared plus 1, and then minus 3, and then this entire business over 3, okay, plus c. And then our final answer is simply going to be the square root of x squared plus 1 times x squared minus 2 over 3, okay? And there goes your final answer, much faster than the other method, and less room for error, okay? So that's that. Good day, students. Welcome to part 3 on my integration by parts, advanced table integration series. So let's go ahead and take a look at the second example. This is a continuation of the two-part series on advanced table integration. So for number 2, we're to evaluate the indefinite integral of cosine of the natural logarithm of 3x. Okay, now this problem is an integration by parts problem, but in order for us to do integration by parts, we have to do a u substitution first, and then we're going to apply integration by parts. Okay, now I'm going to call this a w substitution because I'm going to be using u substitution later, and I don't want us confusing our u's if I use it twice. So let's call the inner function right here w. So I'm going to call w equals the natural logarithm of 3x. Now I'm going to exponentiate both sides using e as the basis of exponentiation. So we have e to the w is equal to e to the natural logarithm of 3x. Okay. Why did we exponentiate both sides using e? Because it gets rid of this natural logarithmic function, and upon differentiation, I can end up with a multiple of dx. So on the left side, we just have e to the w. On the right side, the e and the ln's cancel out, so we have 3x. Now let's go ahead and differentiate both sides. If I differentiate e to the w, I'll have e to the w dw. On the right side, if I differentiate 3 to the x, I'll just simply have 3 dx. Now I need dx isolated so I can substitute it. So I'll basically divide both sides by 3. Both sides by 3. So we have, and work sideways, e to the w over 3 dw is equal to dx. Okay, so I'm going to make a substitution using this equation right here, and let's see, this equation right here. Okay, so let's go ahead and rewrite our new problem. So the original problem we had, the integral of cosine of the natural logarithm of 3x dx using our w substitution now becomes the integral of cosine of, instead of ln x, we're now going to have w, and instead of dx, we'll have e to the w over 3 dw. Okay? Now you might get tempted to factor out e to the w over, to factor out the 3 here. You could do that, but since you're making multiple substitutions, it's good to refrain from that, or else it makes the process much complicated when we're doing our integration by parts. So the smart strategy here will be to just leave it in this form, okay? Now we can clearly see that this is an integration by parts problem, and I'm going to evaluate it using my advanced tabular integration method, all right? So using our Lipet rule, we know that exponents come before trig, so our u is going to be e to the w over 3, and our dv will be cosine w, okay? So I have u and dv. Now the method I'm using right now, I went over it in detail in my previous installment of this two-part series, so please go back and review that if you do not understand what I'm doing right now, okay? So my u is going to be e to the w over 3, and my dv is cosine w. All right, so we're going to keep integrating until we end up with a multiple of cosine, until the cosine function shows up again. So let's go ahead and do that. If I integrate cosine, I have sine w. The question is, is it a negative or a positive? Since if you differentiate sine, does the sign change? The answer is no, so it stays just the way it is, all right? So let's differentiate this. The derivative of e to the w, you can factor out 1/3. It's still e to the w over 3, okay? Now we're going to keep integrating until we end up with the cosine function. So if you integrate cosine sine w, you end up with cosine w. Is it a negative or a positive? Well, if you differentiate cosine, does the sign change? It does, because the derivative of cosine is negative sine. So we have to put a minus here to compensate for that sign change. If you integrate this, you're going to end up with same thing, e to the w over 3. So you stop here, stop integrating and differentiating, because we now have a complete cycle. We're back to cosine. All right, so let's put in our arrows for the tabular integration. This is uv, and then this is uv. And then we're going to group our last row together, like this. The last row. Like I said earlier, I went over this method in the earlier tutorial, so you can take a look at that. And then the sign, we know that the sign behavior for tabular integration, this is plus, and then this is minus for the uv, but this minus also has to be distributed to the vdu, so we put a minus here. This minus also goes here too, okay? So let's go ahead and set up our integral. We're going to have, let's see, so we have the integral, the original problem, the integral of cosine w times e to the w over 3 dw is equal to the first pair. That's going to be multiply these two, and the sign is going to be positive, so it's going to be e to the w sine w over 3. And then the next pair, these two minus, this minus times the minus makes it a plus e to the w cosine w over 3. And then for the last portion, since we're going horizontally, we're going to have an integral. It's going to be an integral. So if we multiply minus times minus times minus, 3 minuses is going to be a minus, minus the integral of b du, which is going to be e to the w cosine w over 3. Okay, dw. Now, if you notice, this integral and that integral are identical, so we can combine them. So what we'll have here is we're going to add the integral. I can rewrite this as cosine w times e to the w over 3. Same thing. And then add it on here also. So the integral of cosine w times e to the w over 3 dw. Alright, so when I combine those two, let's go ahead and do the combination. I'm going to have 2 times the integral of cosine w times e to the w over 3 dw equals this business right here, e to the w sine w over 3 plus e to the w cosine w over 3. And now to get rid of this 2, because we didn't have any 2 in the original question, what we'll do is we're basically going to multiply both sides by 1/2 to get rid of that 2. So let's go ahead and do that. You multiply this side by 1 over 2, and multiply this entire expression on the right side by 1 over 2. Okay? Now if we simplify, we're going to have the integral of cosine w times e to the w over 3 dw equals, if you distribute, you have e to the w sine w over 6 plus e to the w cosine w over 6. Okay, just multiply the denominators plus c. So the question now is, are we done? The answer is no. Remember, the original problem was in terms of x, so we have to substitute our w equals ln 3x back into our equation and simplify it as much as we can. Okay? So the original problem, the integral of cosine of the natural logarithm of 3x dx equal to, it becomes e to the, instead of w, it will be the natural logarithm of 3x. Sine, instead of w, it will be sine of the natural logarithm of 3x. This entire business, let me draw that again, 3x. And this will be over 6. And then same substitution process applies to this term right here. So we'll have e to the natural logarithm of 3x instead of w, cosine the natural logarithm of 3x, because that's what we substituted for w, divided by 6 plus c. Okay, now let's see, can we simplify this? Yeah, we can simplify this. The ln, the e and the ln's can cancel out, the inverse operation, so we can cancel out e and ln here, and then e and ln here. So that's going to leave us with, let's move that up. It's going to leave us with 3x sine the natural logarithm of 3x divided by 6 plus 3x cosine the natural logarithm of 3x divided by 6 plus c. Okay, and you notice 3 can go into 6 in both terms, so our final answer is going to be x sine of the natural logarithm of 3x over 2, or you can write it as 1/2, makes no difference, over 2 plus x cosine the natural logarithm of 3x over 2, also because 3 goes into 6 two times, over 2 plus c. All right? So that's the value of the indefinite integral of cosine of the natural logarithm of 3x dx. So that's that.